So hi guys, I hope you can hear me. All right, I think it is the case. Fantastic, fantastic. So hi guys, thanks for coming today. It's good to be part of this event once again. So thanks for the organizers for making this up. It's always amazing and a pleasure to be here. So as you can see from the slides, we're going to talk about dynamic libraries and some advanced concepts and conventions that we need to be aware about so that we never break code compatibility again. So let's get more familiar with the problem and bring everyone on the same page. All right. So let's imagine, for example, that we are making a new library. You can think of any kind of code. Maybe it's image processing, maybe it's cryptography, or even a Bitcoin library. Think of any library code that you are gonna sell to your clients. In our example, it is a very simple library called libusermanager version 1.0.0. And this library can list connected users on the system. Now that we have some awesome code, some nice code, let's compile it. Let's add some, or maybe you can even add some stripping to avoid reverse engineering. And then you can deliver this to your clients. Your clients are going to build their binaries and link to your library, which is required by their algorithms. It works fine, and they are able to list connected users on the system. Then they are going to sell their binaries to their respective customers, which is quite perfect at this point. And then, surprise, surprise, few months later, you have discovered a bug. Or maybe the client has requested some changes, or maybe wants you to introduce a new feature. But your client has some constraints. He can't afford to recompile his old binaries because it takes time and it takes money. He just wants his customers to take your library, copy-paste it on the target file system and work on the fly. He doesn't want to handle many different versions of the library. He just wants to use the latest library, which should work with all versions of his binaries. And you know, this is a really tough problem if you don't know the things that we're gonna learn today. So what do? You make the changes, you create a new version of the library, and of course, it works fine with the new compiled binaries. However, some of your clients' customers who are still deploying with the old binaries downloaded your new library because they know it has some bug fixes, maybe zero-day vulnerability fix, and they try to use it with the old binary. And this doesn't work because it's still looking for version 1.0.0. It's too risky for them to switch on this old version of the library. So everyone wants to use your new library. Alright, of course it doesn't work. It shouldn't work. Because if you look inside the client binary, let's say for example the first version, you're gonna see in the DT needed field that it's looking for version 1.0.0. That's what the loader is going to look for to try to locate the library on your system. And by the way, we're going to introduce later how the loader locates the libraries. What about the second binary? It's the same thing. It requires version 1.0.1, and things are gonna get really bad with time with different libraries and binaries versions. And this is exactly what is called the library versioning problem. You know what? Today, we're going to take a look to the two commonly most known conventions used to create maintainable dynamic libraries, which can be linked from any binary version without any recompilation. And that's amazing. Alright, so before going further, that's a little bit about me. So my name is Bekalem Jugurta and I am an embedded systems engineer and I work for Smile Open Source. We provide various services to our customers. I work in the embedded and IoT unit where we build software for embedded and IoT devices, going from the kernel to the user space, and then managing everything from a cloud provider like AWS or Azure. So that was a bit about me. So let's jump right to the presentation's core and discover cool things to help us build in better library code. Let's start with some background. So what are static libraries? Static libraries are just a bundle. They are a bundle of object files, and we use mainly the AR tool, which is available in your toolchain, to handle most static libraries related operations, which goes from creating the static library to even things like removing or appending new object files into a pre-existing static library. Of course, static library symbols are ingested into the client binary and become part of the binary. The naming format convention is having the lib as a prefix and .a as an extension. On the other side, we have dynamic libraries. Unlike static libraries, they are separate files, which must be delivered along the executable requiring them. Dynamic libraries enable code sharing where only one instance of the library is loaded into memory with multiple processes using that same instance at the same time. The naming convention format is having lib as a prefix and so as a file extension. In real situations, library version information is required. This is required because we need to keep track of the different versions and changes made so far. That's why we usually add the MMP notation, which stands for major, minor, and patch numbers respectively. And by the way, you can convert at any time a static library to a dynamic library. Just use the AR tool to extract the static library's content and then build the final dynamic library from the object files, which works fine most of the time. So before closing the introduction section, we need to revisit the compilation process. For static libraries, use GCC to generate your object files and then AR to generate the final static library. For dynamic libraries, you generate your object files using the fpic compiler flag and then you link using the shared linker flag. I have one important remark. Some people think that the fpic is what makes a library dynamic. Absolutely not. It's the shared linker flag which makes a library dynamic. The truth is that you can compile static libraries using the fpic compiler flag. The situation is mandatory, for example, when static library needs to link to a dynamic library. We have even more. You can create a dynamic library by removing the fpic, but it's going to result in a library using something called load time relocation, which means that multiple copies of the library are going to be loaded into memory for every process that requires them, which means that we lose the advantage of code sharing. A last remark. that I would like to share with you is that you can convert a dynamic library to an executable, which means it's going to behave as an executable and the library at the same time. For example, we have glibc. glibc is a good example of this. Here is a screenshot of glibc on my system. You can see that we can run it actually. Maybe this is something that may interest you to do for your customers or for yourself. All right. So far, so good. So now that let's start and jump right away to the core of the presentation. So in section 2 and section 3, we're going to take a look to the two commonly most used methods for creating maintainable dynamic libraries. Let's start with the first one called the SONAME versioning scheme. We have seen the general form of dynamic libraries naming convention, which uses the major, minor, and patch numbers. So what the SONAME convention says is that binaries should be linked to a library with a name that only contains the major number. This is what the SONAME is all about. SONAME is just the library name plus the major name, plus the major number, sorry. So at this point you would ask, hey, but this violates the rule that we need to have the complete version information with major, minor, and patch numbers. And the answer is yes. But don't worry, we're going to keep that. Because technically, the SONAME is just a soft link, which is named with the library name and the major number. All your binaries should be linked to a soft link. And then the soft link itself points to the real library with full version information. Once you have the new library release, you just have to update the target to which the soft link points to. And this is great because you don't need to recompile the binary anymore. So this is important. We have to keep this in mind. As a general rule, never link your executables directly with the library. Carry in full version information. Of course, the dynamic library itself must be compiled in a certain way that we're gonna see later for this to work to support the SONAME method. So the next question is this really used in our systems today? And the answer is yes. Just take a look to your system's libraries. Let's say, for example, the libarmor.so.1. This is what? This is a SONAME. This is a soft link SONAME, which points to the real libarmor library. But as I told you in the previous slide, the library must be compiled in a certain way to include the DT SONAME field. Here is an example. However, there is one limitation with SONAME method. We are only limited to minor and patch number changes. So if you break your API or need to make a new release with a higher major number, SONAME is not going to work. We're gonna take a look to another method, to much more advanced method, which doesn't have any limitation, but requires a bit of tweaking the library code in the next few slides. But for now, we stick with the SONAME. Right, so maybe during compilation, you may need an extra soft link. Another soft link, yeah. Let's take a look again to the previous linking flow. So the binary which links to the soft link, which refers to the dynamic library. So without this extra soft link, we have to compile the binary as shown in red. So we need to pass the complete name of the soft name explicitly. But if we try to introduce this extra soft link, then we just can compile as shown in green. This is what we like to use most of the time. So the global picture becomes the binary, which requires the extra soft link during the build time, which points to the soft link SONAME, which refers to the library with full version information. So before we go to practice, let's revisit this. So SONAME is a super simple convention which is really effective. We don't need any code changes inside the library code to support it. It really works on the fly. All your binaries can link without any recompilation to the latest version of the library, just by updating the target referred by the softlink SONAME. So you just have to update the green arrow and it's gonna work fine and you're done. So let's practice. Let's say, for example, that we have this request document to create a dynamic library. So the library defines one function called getFileStats. And this function accepts a string file path. And getFileStats should return statistics regarding the provided file path. The function needs to check if it is a valid regular file to return any kind of statistics. Otherwise, it should print invalid file. So let's see this in practice. So in our library, we define the header file, which contains just some basic imports and declares the function prototype. And then the function implementation, which uses the start interface to get statistics about the file in question. And then there is a check. If it is a regular file, we say we print the statistics. If it's not, we just say it's invalid file. All right, let's compile this. Let's see how to compile this. So as we have said in the previous slides, dynamic library should be compiled in a certain way to support the SONAME method. So this is how compilation is done. Just add the linker flag SONAME and you're gonna be good. Now, if you look inside the library, you should see the DT SONAME field, which is going to propagate later to the executable binary that links to your library. SONAME is well known. This is why it has a big support from various tools, even the LDConfig, which is used in Linux as a way to locate required dynamic libraries dependencies of an executable. We're going to talk about LDConfig later. But in this slide, what we should learn is that using the LDConfig, one can extract the SONAME softlink from the library. And then you just have to add the extra softlink required for compilation and then compile your binary. And you're done. That's amazing. Let's upgrade our library content. So here is another request document for other changes required for the library. So now we need to introduce a new function called getFilesInFolder, which receives a path argument referring to a folder. The function should traverse the folder and list its content. We are also asked to fix a new line issue in the previous version of the library. So here is how it works. So that's what the function looks like. So we use the opendir to open a directory and then use the readdir to list its content. This is just system programming. If you're interested in this, you can read the Linux System Programming 2nd edition by Robert Love. And then at the end, we just have to close the file descriptor. All right, I think it's time for the demo. Well, let's do it. So just remember, I'm going to show two different versions. So the first version with the getFileStats, and then I'm going to show the second version with the addition of getFilesInFolder. So I'm going to put this aside. So this is the first version which only has the getFileStats. I'm going to compile this and we see how it's done. So I'm going to compile the dynamic library with the SONAME linker flag. Amazing. Just before going further, I just want to show you something using the readelf. The readelf v library maybe it's capital V. No, not this one. What was again? The read elf D. Sorry, it's the D. Yeah. Yeah. So using the D, we can see the DT saw name field, which has been inserted into the library, and this is going to be propagated into the client binary. And then I'm going to use the ldconfig to create the softlink saw name. So now we're going to see that there will be a softlink which points to the library, the library, as you can see. Yeah, good. And now I'm going to create the extra softlink used for build time, and then I'm going to compile the binary. I'm going to execute the binary. It's telling me that I need to feed it with a file name. So I'm going to choose ls, for example, and it works. We see that it's returning some file statistics like the inode number. But we see that we have a small issue because when it prints the statistics, it doesn't add a \n. So we need to fix this in the next version of the library. So let's move to the next version of the library. So from the slides, it's version 110. So let me move to that version 110. Okay, great, amazing. Okay, great, amazing. So I'm going to do the same thing. It's almost the same steps, so I'm going to do it really fast. And then I'm going to recompile the binary. So if I execute this, it's telling me that I need a folder. And now it's listing the current files in the current folder. Okay, great. So if we take a look to the source code of our library, we can see that we have the two different functions. The first one, which is getFileStats, which has a fix for the new line issue, and which introduces as well the getFilesin folder. So I'm going to take this library. I'm going to try to use it with the old binary. This is a good test to do. But for this, I'm going to remove the old library. In such a way, if I start the binary, it's not going to find the right library. Why? Because we need to update to update the soft name to point to the correct library location. So if I check this again, read link lib.so.1, it's pointing to the new version, which is 110. So now if I execute the binary, yeah, we need to feed it with a file, and we can see that well, it's working well, it's displaying statistics, and we have the fix for the new line. And as you saw, I didn't have to recompile the binary itself, and this is really amazing. All right, let's get back to the presentation once again. All right, so until this point, we have seen the saw name convention, which is kind of pretty straightforward and simple. However, it's limited to the major number. So once again, if you change the API or methods definition, your binaries won't link anymore without recompiling them. That's why we need a more powerful method. And this method is called the symbol versioning. And I can tell you that you can make any kind of changes and it's going to work fine. On the same library code, for example, you can have multiple symbols you can have the same symbol defined multiple times. For example, you can have both of these two symbols and it's not going to generate a compilation error. We have even more. you have the power to say explicitly which one is going to be used for the new libraries and which one is going to be used for legacy. And the best thing about this method is that you can set the symbols visibility. This is important because on Linux, library symbols are exported by default. So you can choose what you would like to export to your client's binaries. Well, symbol versioning scheme is built on the top of two concepts. So the first one is a special script file called version script. And this script enables us to change the behavior of the linker. This is what a version script looks like. We're going to learn the general syntax in the next slide, but for the most curious of you, the global keyword defines which functions are going to be exported and made visible for the client binaries, and the local keyword defines which functions remain hidden. The second concept is called the symver directive, which is required only when you have symbol conflicts. So, just to make it clear, we always need to write a version script. And for the symver directive, it's only required to handle conflicts. So here is an example of how to compile a library using symbol versioning methodology. We can see in the red that we pass the version script file to the linker. Amazing. Let's go to the next slide. Let's see more about this method. So let's say, for example, that we have a library called libmycipher version 100, which defines three different functions. With the function generate random letter, which must be local and not exported to the binaries. So how to write this in a version script? So this is what it should look like in a version script. For every new library release that you are going to make, in which you have introduced new functionalities or broken the API, you're gonna add something called a node name. There isn't a real standard on how it should be named, but usually just take the same library release name. So in this example, for example, it's libmycipher 100, all in capital letters. And then you can use the global and the local keywords to set the visibility. For example, in our case, we have the shift row and generate hash key, which are going to be exported to the binary, but generate random letters will remain local. Well, let's add a new function to our library. Let's say, for example, we add the function select cipher. This is how we should edit the version script. So all we have to do is to append a new node name. In this case, it's libcipher 110, and say that select cipher is global. So at this point, maybe you would ask, hey, but this means that the version script is there only for symbol visibility. This is something we can achieve as well using GCC directives. And if you ask this question, you are definitely right. But that's not all the story, because until now, we didn't have any API change or duplicate symbols. That's why in this slide, we're going to see the second concept of symbol versioning, which requires the version script. So let's say, for example, that initially the first version of the library, we have a function called getRandomPassword, which translates to this script, to this version script. And then later we need to break this API and replace it with the new interface, but we need to keep legacy as well. So this translates to this version script. Now, because we have two symbols, we're going to have a conflict. So how to handle this using the symver? So in the body implementation of the two functions, we should add the SymVer directives. Something important in the function implementation is that we change the function name. And in the SymVer directive, we map that name to the duplicate symbol. And we must indicate to which node name in the version script our function is related to. We're going to see a practical example to understand this more. But what I want you to see is that there is a bit of difference between the two SymVer directives. So in the first case, for example, we only have one @ symbol, and on the second case, we have two @ symbols. So the double @ symbol tells the linker to use the second function for all new compiled binaries. This is important. Well, so if we take a look inside a library compiled using the symbol scheme, we would see three different sections. So the first one is called the .gnu.version, which presents a brief summary of the symbol versions. And then we have the .gnu.version.d, which reflects the full versioning information for this library. And then we have the GNU version R, which presents the version information for all libraries that our library is referring to. All right, it's demo time. And let's go to the symbol versioning method. It's the third one. All right, great. So maybe I can actually close all these. Yeah, good. So I'm going to open my library, and we can see something important, that I have a duplicate get random password. But because I'm using the SymVer directive, so I have replaced the duplicate symbol with another name. And on the SymVer directive, I'm mapping this new name to the duplicate symbol. And we have to, of course, we have to say as well in which version, to which node name version in the symbol script this function belongs to. All right, let's close this and compile. So first, I'm going to compile the dynamic library, and then I'm going to compile the dynamic library using the version script. As you can see, I'm passing the version script. And then I'm going to create the extra soft link used for compiling. Amazing. And then I'm going to compile the binary. I'm going to run the binary, and surprise, it works perfectly. So now if I look inside the binary using the readelf, I'm going to see that the version information are actually propagating to the binary. All right. We are perfect in time. Good. So let's get back to the presentation. So now let's start a new section and discover something else, something really quite important, I think, something important to know. So for every binary needs to load some dynamic libraries. But how does Linux locate these libraries? Well, Linux has a predefined searching locations that we need to be aware of. Just to make things clear, it's not enough to put your libraries in the current directory and expect Linux to use them. This is what Windows does, but not Linux. So on Linux, we have this. We have the LD preload, which is an environment variable, which has the highest precedence in the system. So this is the first place where the loader is going to look. So if you add your library to this variable, the loader is going to find it. But there is one bad thing with this, is that every time you add the library to this, it's going to be injected into the process address space for every new process, even if it doesn't need it. And this is really bad. And then the workflow differs slightly depending on whether or not the run path is defined or not. By the way, the run path is just a field in the binary which indicates where to find a given library. It contains a path to a library. On the other side, we have the rpath. Rpath is the predecessor of the run path. Normally you won't use that today, but it's good to know that it exists and how the library search mechanism is affected. And you have as well the LD library path. This is another great environment variable. So if you want to test something quick, just use this one. It's safe, it's good, it's better than the LD preload. And then you have the LD cache. When you install a new package using apt, for example, then Linux calls the ldconfig at the end of the installation. And ldconfig is passed the path of the folder containing the required libraries that the binary needs. ldconfig caches the library path. This is going to become more clear in the next slide. And then on the last step, you have the classic /lib/user/lib folders. So as you can see, Linux does not look inside the current folder. If you wanted to do so, then you can, for example, set the run path field to point to a library in the current directory. So here are a couple of useful information to know. So the first point shows that using the patch elf utility, you can change the run path of a binary without recompiling it. This is good for testing or for quick hack maybe. And the second point shows where ldconfig stores the paths of the library. So you can see the list of all the files that actually store the paths to different folders containing the required libraries on your system. And then the third point is kind of the result of the ldconfig scanning. So the file that you can see, which is the /etc/ld.so.cache, is generated by ldconfig every time it scans a directory. So every time it scans a directory, this file is updated. You can see that this file contains the name of the libraries that ldconfig has found. So ldconfig is a really important point in the Linux library searching mechanism. Alright, so here we come to the final point. So we have seen a lot of things about dynamic libraries. Use them in practice to write really good and maintainable libraries. You can choose to use soname or symbol versioning depending on how you expect to maintain your library. Soname is limited to major number and version symbol is not limited. And the last point is that we have mentioned is that Linux has a predefined locations and mechanism that it uses to locate your libraries. It's not enough to put your library inside the current directory, so you have to know how this works. Here is a couple of links that may be useful to go further. Well, especially the second one. The second one, it's a great book. It has really full and a lot of details. You should check this. Well, this is the end of this presentation. I really hope that you have enjoyed it.